Hello, everyone. I'm Wang from the Chinese University of Hong Kong. I'm going to present the paper separating data file block invalidation time inference for write amplification reduction in log structured storage. This is a joint work with our collaborators from the Chinese University of Hong Kong and Alibaba Group. We motivate the problem from our production cloud block storage system, Alibaba Cloud enhanced SSDs. Alibaba Cloud eSSDs use the log structured design atop a distributed storage platform named Pangu, which provides append interfaces for the upper layer applications. They are backed by flash-based storage and achieve around 100 microsecond latency and up to 1 million LPS. Each eSSD is a block level volume as an append-only log that is subscribed by the users. Each log contains segments of hundreds of megabytes, and each segment is further composed of blocks of several KB. Those blocks are identified by logical block addresses, LBAs. The log structured storage needs garbage collection for space reclamation of the stale blocks that are invalidated by the updates. We abstract the GC as a three-phase procedure. Upon the system garbage proportion, which is the percentage of the invalid blocks in no blocks, exceeds a threshold, for example, 15%, the system triggers GC. GC selects segments according to some algorithm. For example, greedy selects the segments with the highest garbage proportions. GC rewrites the valid blocks inside the segments and then deletes the old segments so that the occupied space can be reused. This procedure incurs write amplification due to the repeated rewrites of the valid blocks, which further leads to reduced flash storage lifespan and provision bandwidth that can be sold to the users at Alibaba Cloud eSSDs. In this paper, we explored data placement for WA mitigation. We assume that each write or update in the workload to an LBA first introduces one user-written block, and then GC may rewrite the block and introduces several or multiple GC-rewritten blocks. Thus, the WA equals to 1 plus the number of GC-rewritten blocks over the number of user-written blocks. As a result, in the right bottom figure, data placement sees two types of blocks: user-written blocks and GC-rewritten blocks. It assigns them to different open segments. The open segments do not exceed their maximum sizes and are appendable. GC will collect the sealed segments that reach their maximum sizes and rewrite the valid blocks as GC-rewritten blocks. The aim is to separate blocks into groups according to their properties, such that the blocks in the same group are more likely to be invalidated together. And thus, the system can produce high GP segments for GC, which means less rewrites of valid blocks. We propose SepBIT, which separates blocks by the inferences of the block invalidation time, abbreviated to BIP. Its method is established on effective bit inferences based on mathematical and trace analysis. It separates each set of user-written blocks and GC-rewritten blocks by bit inference. SepBIT is now deployed at Alibaba Cloud eSSDs. We verify its effectiveness via extensive trace analysis and prototype evaluation. We first discover an ideal data placement scheme that achieves the minimum WA of 1 with the knowledge of bits. Its idea is to strictly place all written blocks based on their invalidation orders, such that GC can select the segments whose blocks are the earliest invalidated, with no rewrites of valid blocks incurred. We observe that the optimal result of the ideal data placement scheme stems from its two impractical assumptions. First, it needs to know the invalidation order of each written block. Second, it needs to reserve memory or storage space for all the written blocks in advance. As a result, an effective practical method needs accurate estimation of the bit of each written block, and in the face of limited memory or storage space, it has to group blocks of close bits together. We further conduct trace analysis based on the block lifespan to derive 3 observations. The lifespan is defined as the number of bytes written in the workload from when a block is written until it is invalidated, or until the end of the trace. We use Alibaba Cloud block traces that span 1 month period in January 2020 and select 186 write-heavy volumes for validity of the analysis. Those volumes have large write working set sizes and large write traffic sizes. Our observations are also validated on Tencent Cloud block traces. Observation 1 states that user-written blocks generally have short lifespans. We found that the majority of volumes have high percentages of user-written blocks whose lifespans are smaller than a small percentage, for example, only 10% of the write working set sizes. In contrast, GC-rewritten blocks generally have long lifespans in that they survive after the GC to their corresponding segments. Thus, the user-written blocks and GC-rewritten blocks have different bit patterns. Observation 2 says that frequently updated blocks have highly varying lifespans. We see large variations in different groups of frequently updated blocks in each volume. Observation 3 says that rarely updated blocks dominate with highly varying lifespans. We found that the lifespans of the rarely updated blocks span both long and short ranges. These observations suggested that temperature-based scheme, for example, using access frequencies, are ineffective in bit inference. Without using temperature-based metrics, SepBIT first separates all written blocks into 2 groups, user-written blocks and GC-rewritten blocks, because they have different bit patterns. SepBIT further separates each set of user-written blocks and GC-rewritten blocks into 6 classes in total. For the user-written blocks, class 1 stores the estimated short-lived blocks because they have similar bits if they are written near the same time. Class 2 stores the remaining long-lived blocks because they span large bit ranges. For the GC-rewritten blocks, class 3 stores the estimated short-lived blocks that are identified in user-written blocks. For the remaining blocks, SepBIT groups them into 3 classes with similar bits inferred. Although we assume 6 classes here, we validate the WA mitigation of SepBIT is not sensitive to the number of classes. To estimate the lifespans and thus the bits for the written blocks, we conduct probability-based analysis for both the user-written blocks and GC-rewritten blocks. For the user-written blocks, we try to use the lifespan of the invalidated old block to infer the lifespan of a new user-written block. Our intuition is that any user-written block that invalidates a short-lived block is also likely to be a short-lived block. Specifically, we investigate the probability of the lifespan of a user-written block being smaller than the threshold U0, given the condition that the lifespan of its invalidated old block is smaller than V0. We find that the conditional probabilities are high for different combinations of small U0 and V0 in Alibaba Cloud block traces. This finding indicates that the intuition holds. If the invalidated block has short lifespan, we can say that it is highly likely that the new user-written block also has short lifespan. For GC-rewritten blocks, we try to use the age of the GC-rewritten block to infer its residual lifespan. The residual lifespan is defined as the number of written bytes in the workload since the rewrite of the block until the invalidation of a GC-rewritten block. Our intuition is that any GC-rewritten block with a smaller age is likely to have a short residual lifespan. Specifically, we studied the probability of the residual lifespan of a GC-rewritten block being smaller than threshold R0, given the condition that its age passes G0 when being rewritten. We found that the conditional probabilities drop significantly when G0 increases in Alibaba Cloud block traces. This means that GC-rewritten blocks for different ages can indeed have distinguishable residual lifespans, and thus we can effectively infer the residual lifespans while their ages. We implement SepBIT as follows. We set the threshold of the separations according to the workload on the fly. Specifically, we monitor the segment lifespan, which is defined as the number of written bytes in the workload for a segment since its first append until its collection. We compute a value L, that is the average segment lifespan of the collected segments in class 1 for each 16 collected segments. Then, for classes 1 and 2, which store estimated short-lived and long-lived blocks respectively, we use L as the lifespan threshold according to the lifespans of the invalidated blocks of the user-written blocks. For classes 4 to 6, which store the GC-rewritten blocks that are not previously from segments in class 1, we use 4L and 16L as the age thresholds according to the ages of the GC-rewritten blocks. We also achieve memory efficiency in that we only need to track the blocks whose ages are less than L in memory, with the age information of all the blocks in the flash storage, and they can be retrieved along with the blocks during GC. We conduct both trace analysis and prototype evaluation. We use 186 volumes in Alibaba Cloud block traces and vary segment selection algorithms, segment sizes, and GP thresholds for GC. We compare SepBIT with 11 schemes, including 8 existing schemes proposed in the last 2 decades, and feature knowledge, which stems from our idea data placement as an Oracle scheme here. We also build a C++ prototype and use emulated zone storage devices because it shares the same storage abstraction as Alibaba Cloud ESSDs, and it is easier to reproduce. SepBIT outperforms all existing schemes under all combinations of the settings. We present the results on the cost-benefit selection algorithm here. It reduces overall WA by 9.1 to 20.2%, and it approaches the overall WA of the Oracle scheme feature knowledge. SepBIT also realizes the lowest 75 percentiles among all existing schemes. We prototype SepBIT and compare it with the best candidates of existing schemes found in our trace analysis results. On 20 write-heavy volumes, SepBIT achieves the highest throughput for 25th and 50th percentiles, with 20% higher than the second best. To conclude, SepBIT is a novel data placement scheme that mitigates WA in log structured storage via bit inference. It infers bit patterns based on trace analysis, and it is now deployed at Alibaba Cloud ESSDs. For more details, please see our paper, technical report, and source code. Thank you so much for your interest and attention. I welcome all your questions.